So, good evening, everyone. My name is Nader Elm. Again, I want to thank FirstMark for inviting me to come over here. The first thing I'll declare is I'm British, so I'll say that so you can calibrate to my weird accent. The second thing I'll declare is I don't know how we came up with this title. Even closer. Okay, right. I don't know how we came up with this title, but Autonomous Aerial Robot Software Enabling Underground Drone Mapping. It's a bit of a mouthful, and we'll start unpacking components of that through the presentation. The final thing I'll declare is I've breached all rules about slide numbers, so I'm hoping you can fasten your seatbelts. Hopefully no one's going to get hurt. So, when we started the company, we really kind of were trying to identify a trend. And one of the trends we saw was that big data was obviously very big, but it was focused on what we call digitally rich industry verticals. And by that we mean industry verticals whose operations, just by their very nature, are generating volumes of data. So the data wasn't the problem, the analytics of that data was. So all of these lovely big data tools start coming to the fore and impacting these industry verticals quite dramatically, and some great stories to tell over there. But conversely, there are some multi-trillion-dollar industry verticals who haven't been able to enjoy the big data revolution, not because they don't want to, but basically because the data acquisition, the collection of the data itself is the problem. And that's basically where we started focusing our effort. And the reason is because getting data in these situations is really, really hard to do. Those industry verticals, you will no doubt visualize and start thinking about as those backward industries that really haven't innovated much over the past, let's say, 100 years. But that's basically because the environment that they operate is very, very dangerous and tricky or vast, discontinuous operations, and very, very difficult to get the data. So in other words, it's expensive, it's infrequent, and oftentimes very inaccurate. So comes the drone revolution, and this is what we saw in the earliest variations of the drone world. You know, there's nothing like kind of coming up with a new data acquisition platform that cuts the people that are paying you for your services. So the drone was the first platform that came out that could operate in three-dimensional space. I mean, we already had some ground-based robots. For those of you familiar with Kiva, that's been kind of driving a revolution in Amazon. But in the other industries like mining that we'll focus on, these vast three-dimensional spaces are very, very difficult to navigate, and you can't do that just with a ground-based robot. So hence the drones started coming to the fore. And then drones started getting more intelligent, but there's still a big problem with them because their intelligence is somewhat slightly limited, because in open spaces like this, you tell it to go from GPS waypoint A to GPS waypoint B, and it will do exactly what you tell it to do. The problem we have with these smart drones is the fact that they literally go from waypoint to waypoint and have no awareness of anything around them. So you can't use that as a method for data acquisition either. So what we really want, if we dare to dream, it's going to be something like this. And I'm shamelessly, I was told that we could cut out bits from the video, and this is one of the things we'll cut out is I've shamelessly borrowed from 20th Century Fox and Prometheus, where they release these drones, these orbs, that go through an alien ship. So there is no infrastructure in the space, there is no prior map, and the robots are intelligent enough to flow through this alien spaceship, building a three-dimensional model of the map. And this is exactly what people are asking for. A handsome, rugged Englishman and the three-dimensional map that comes with it. So essentially, keep that in the back of your mind. So what have we just seen over here? If we were to kind of break it down, basically full autonomy. And that was one of the words in the title, and we'll kind of dig into that a little more deeply. But if you've got full autonomy on one vehicle that can go in these alien environments. By alien, I don't mean off-world. I mean environments that are really, really harsh. They're unknown. They're dangerous. And if you can put them into real-world environments with very, very little training, so you just basically have to give it very, very high-level commands like go explore, And if you can get them to collaborate with each other so that they can take over a mission and in an expansive volume, that is basically what we've seen, and that is what people are asking for. Whether it's a warehouse, whether it's a mine, whether it's a construction site, the demand is still the same. So autonomy, obviously, the challenge is it's very ill-defined as a word, and therefore everyone claims to have it. So I'm going to double-click on that for a little bit, and you're probably saying, no, Nader, don't be daft. We've heard about autonomous cars, and we've had these 5 levels of autonomy defined. And what we're seeing over here is from the Society of Automotive Engineers. They're the ones who define the 0 to 5 levels. And basically what it says is with high levels of autonomy, the driver becomes more transparent. And also, obviously there's greater autonomy in the car so that you don't need the driver. But the interesting thing to note is that that is very focused on the driverless car. Because one of the things it considers is really just one dimension of a 3-dimensional problem, which is basically how do you reduce the dependence on the human operator. But in terms of environmental difficulty, it drives on roads, very well-structured environments. Now, it's still populated by irrational things like people, but it's relatively structured. So when the GPS coordinate tells you that you're roughly in this space, if you're in a building, then you're kind of saying, okay, with a high level of confidence, that's probably not true. I'm probably on this road. So that's one thing. The environmental difficulty, it's not as severe. And then the other one is mission complexity. Bottom line, not to disparage what Waymo and Uber are doing, bottom line, what you're doing is you're getting from point A to point B. However, there's a lot of other missions where you'll have to give a lot fuzzier kind of instructions, like go explore. You basically have to give it some very, very broad boundaries in terms of what the mission is, and then the robot has to break down that problem and figure itself out. So in a 3-dimensional model, the way we define full autonomy is a little more rigorous, where we kind of say, you've got to make no assumptions that there is any infrastructure around to help you figure out where you are. There is no GPS. There is no motion capture systems. There are no markers or beacons in the environment. It's a completely unknown space. It is completely unknown, i.e. you do not have any prior information to give it. And then the third thing, if you're going to make this thing robust, you've got to assume that you are going to lose communication with the robot at some stage in the mission, but that shouldn't jeopardize the robot's mission. So if you lose communication, the robot shouldn't care, it should carry on. And then you make no environmental assumptions, like there's ambient light. The light might be there, it might go out, but you've got to be able to be resilient enough to those kinds of changes. And then the final thing, full volume 3D environments. Again, the autonomous car lives in a 2-dimensional world. It scans in 3 dimensions, but it knows it can only navigate in 2 dimensions. So that somewhat simplifies it. You make no kinds of assumptions when you're talking about full autonomy. And this is basically a simplified model of what the core autonomy looks like. And any one of these areas, by the way, it breaks out into fragments, and people spend entire PhD theses just exploring any one of these areas. So imagine you've got to have all of this on board the vehicle operating in real time all the time. So that, and in an aerial platform, you've got to imagine you've got to try and get that down to 1.5 kilograms in total weight. Otherwise, you'll never take off. So broadly, I mean, what the autonomy breaks down to is just answering 3 very, very simple questions. The first thing is, where am I? And where am I in relation to my environment? That's something we all do very, very naturally. You're sitting down, you're perceiving your environment, building a map, and you're figuring out where you are positioned in the environment. And then the next thing is, where am I going? How do I get there safely? And that's all the motion planning, control, and navigation. This is basically what it looks like. One of the things I should highlight is we're not a drone company. So what you're seeing over here, as remarkable as it is, and you'll see it in the videos, there's actually nothing remarkable about the hardware because it's all entirely off the shelf. What we work on is the Exyn AI software. It's the intelligence that goes on the robot for it to do the remarkable things that it does. And what we do is we build this system so that we can go and acquire data. The top line is the commercial applications for inspection, surveying, and mapping. And data means different things to different industries. And in deference to any defense customers or government customers, they've got something called ISR. So we enable that to enable intelligence services and warfighters to be more safe, saving lives. So the bottom line technology, so this is what it looks like. How does it do what it's supposed to do? So I'm going to play this video. And we've given the robot a very simple mission to basically hit 2 goal points in an unknown space. And they happen to be on the other side of the wall. And what you're seeing over here is essentially what you and I would see, which is basically the video imagery. And we've overlaid on top of that what the robot perceives of the world in these colored blocks. And then once it perceives the world, these are occupied blocks. So it basically says, this space is occupied, I can't fly over there. In the free space, basically the yellow line is what it determines to be a safe flight path. And what you saw over there, by the way, is someone dynamically moving a rack in its path so that it had to dynamically replan its path to go and hit its first goal point over there. So what's going to happen, as you can see, as it learns more about the space, it's constantly filling out the environment. That's basically what's represented over here in a global map. And what you can't see is basically as it pirouettes, we've actually changed the environment behind it. So it makes no assumptions about the map that it built being the map. So it's constantly updating the map as it goes. And you also notice what we've done is we've actually incorporated on top of this semantic classification. So it recognizes people versus non-people because you can change the behaviors of the robot around people. And so now we're kind of coming to the end point. And basically that's the second goal point, and it'll come to land. What you're seeing over here is basically the map that it builds globally, and that is basically what the customers want, is a global map of the environment. Now, I know what you're thinking. I mean, this is the beginnings of basically the apocalypse. But this is not going to be the case because essentially we are developing for civilian applications in order to save lives, not to kind of enable the Armageddon and the end of the world. So what I'm going to show over here is essentially what's happening in underground mining today. So mining hasn't changed in over 100 years. You go into the mine, you drill holes, you stick in dynamite, you blast, and you create these underground cavities, which are called stopes. And inherently, they're dangerous. You do not want to go into these spaces because the rock fall can be conceivably from 100 meters up. It could kill you if you're in that space. So what you're seeing over here is that's the cavity. And over here is a pile of rocks. It's called the berm, and that's the safety line you're not supposed to cross. What you're seeing over here are the 2 people who took us aside for 1 hour and trained us on exactly what not to do. And one of the things was do not cross the berm. And that's what they're doing, because they have to put this beam into the stope to generate that kind of a map. That is the state of the art. It takes 4 hours, puts 2 people in harm's way, and it generates a decent quality map. It's 50,000 points. So this is basically now what we are enabling, is basically a lot safer way of actually flying in the stope. So this is the robot, and we've given it a very simple mission. Go over the berm, go explore, build a map, come back. So right now, the only time the human is in the loop is giving the instruction. Once you press play, it's literally a play button. The robot takes over, and everything you're seeing right now, the robot is doing by itself. So it's going into an unknown space, and basically it's about 20 meters deep, about 30 meters wide, and this one in particular is about 60 meters tall. So it's it's explored the spot over there, and now it's exploring directly above it. And at this point, we lose communications. But like I said, again, we don't care, because the robot is continuing with its mission relentlessly. And what you're seeing over here is basically the goal points it set itself. It's kind of gone into the center of the stope. Now it's kind of going up. And I'm going to speed this up in deference to the time so that we can So I'm going to speed up. It comes back, and that's it flying back. And this is the map that it builds. A three-dimensional point cloud that you can now visualize and fly through. And this is the first time the mining community has seen their own property in this level of detail. What I can't show over here is the expression on their faces, because they're basically saying, leave this behind, go away, and even though that was a prototype. So we've started actually selling our prototypes with a little bit of support. So, yeah, I won't go. So basically, that is the model that we created of that stope. This is the model that was created by the current state of the art. Again, 3 hours overall to set up, generates 50,000 points. We generate orders of magnitude above that in total of 5 minutes. Set it down, give it the instructions, go, and it's 5 minutes. The consequence of that is not only the fact that you're getting much better resolution of the stope, it's also safer because the surveyors aren't putting themselves into the stope. They spend less time underground. And the more we can actually do this, the more we can actually get people out of the ground, and automated equipment can do the work. And the other thing is also, it's not just about that, it's about the dramatic improvement in terms of productivity that it gains. So what you're seeing over here is the gray is the current state of the art, the model that it builds of the stope, and we've overlaid onto that what we've generated. The difference in volume over here, actually before I say that, the industry is trying to get 1% gains every year. The volume difference over here is 20%. So this has a significant impact on the operations and the productivity. So what you saw, fully autonomous underground mine mapping, using a drone as a vehicle. We basically say it's robotics because it's a robotics that's actually driving the vehicle. But we don't stop there, because as far as the robot is concerned, it doesn't care what environment it's in. This is the same robot in a warehouse application where it's doing cycle counting. What we do over here is we literally put on a barcode scanner, put it onto the robot, and we give it the mission to go run around and scan as many barcodes as it can and geolocate it. So we build a three-dimensional point cloud map, and then we put the barcodes in that point cloud map. So now you know exactly how much of what you got where. And cycle counts are done every 6 to 12 months because it's so expensive, and sometimes dangerous. Now you can do it every day. And then in terms of the other thing that really excites us, it's first responder applications. This happens to be a site directly across the street from us. They're actually demolishing it. So we can actually send the robot on an exploration mission. And again, this is it running around by itself. It's deciding to explore the outside first, and then comes around and starts exploring the interior spaces, building a model of the building as is. And again, we don't make things easy for ourselves. There's all of these structures coming down from the ceiling, which are all hazards, but again, the robot can sense it and avoid and build a model very, very safely in return. So of course, this couldn't be possible. I'm going to speed up a little bit because I just want to leave some time. Yeah, the level of detail, again, you can see all the internal structures over here, some of the HVAC units, certainly the beams. And what we've started working towards is now identifying people. And if you put an infrared camera, now you can identify people who might be under rubble as well. So all of this wouldn't be possible. I'd be remiss if I didn't kind of show a picture of the entire team, which includes the talent as well as the rest of the extended team at the bottom over there. So with that, hand over to questions.
Nader, thank you. That was fantastic. I'm sure we have some questions from the audience. Who's first? Over here, real quick. Oh, wrong way. I need drone tech to know the fastest way to the speakers.
So with these robots, what's the kind of battery life limitations that you have as they're running through the different substructures?
Yeah, So this is actually an older one. So we use off-the-shelf. It's a DJI M210. Naked, it runs about 35 minutes. Once we put our payload on it, it's about 17 minutes.
Awesome.
Yeah.
We got one back here.
Yeah, it seems like you have a Velodyne puck but
Yep,
it's
the VLP-16.
spinning
Yeah.
around an additional axis. Do you get the spinning LiDAR like off the shelf, or are you making it yourself?
No, everything is off the shelf. And that is one of the core things, because we can change up things. So what you're seeing over here is actually, because we're a software play and we can adapt the hardware to the mission, each one of these has a different task. This is meant for mining because it looks up at the ceiling. This is meant for first responders because you're flying outdoors and you're mapping directly underneath you. This happens to be the one for warehouses because you've got a fairly high degree of certainty of what's above you, because this has a blind spot above it. So we fix it, but we know it's going to be safe directly above it. So we adapt all of these things. It's a standard off-the-shelf VLP-16. We gimbal it because we need to have full 3D volumetric vision.
Yeah.
Perception.
So the gimbal part, is that something which you're buying or you're making? And if you're buying it, can you tell me where you're getting it?
I can tell you the people who do know the answer. Yeah, so it's entirely off the shelf. What I can tell you, so it's a motor and a slip ring. The most difficult part is the encoder. And we're using the same encoder that's used in the Mars rover, because it has to be highly accurate.
Great presentation. I was looking forward for this. So the drones basically excel in GPS-deprived areas. Have you, in terms of infrastructure and other areas, have you been thinking of combining the LiDAR with photogrammetry, basic cameras, so you could actually do the inspection, or you're going to focus on point clouds and possibly mesh?
I'm glad you asked that. So we are a sensor fusion. We subscribe to the sensor fusion model. And what you're seeing over here is actually a lot of sensor fusion going on from IMU to the VLP-16. But there are cameras on board the robot as well, so we fold that in. In mining, obviously it's too dark, but in the first responder situation, we exploit whatever we can see as well.
Awesome. Yep. Speaker to speaker, I like it.
Very cool, very cool. So what's the resolution?
Depends. So the VLP-16 kind of gives you 300,000 points every second. The resolution really depends on the angular thing and what distance you're going towards. So one of the reasons we fly so slowly is because we want to paint as many points on a wall. So what we're getting down to right now is 10 centimeters, which in mining is just very, very high resolution. And now that we're going inside buildings, it gets even more dense.
Got one here in the front.
Yeah.
You talked about giving a vague instruction like go explore and sending the drone into an unknown space. Is it smart enough to track how much energy it has left, and will it automatically come back?
So yes, the question was, I had trouble hearing. So is it smart enough to know when it's running out of battery and come back? And the answer is yes. And it's actually better than that, because it constantly, as it's building the map, is looking for the optimal route back. So it doesn't follow exactly the route it took out to come back. So the bingo fuel mark is variable, and when it knows it's going to be, it's got just enough battery to get back, that's when it comes back.
I want the Prometheus example, the drones that was in Prometheus. That's what I want. When is that going to be appearing on your timeline?
The actual floating orb.
Well, and the precision, it can be any drone, doesn't matter, but the speed and the precision and the autonomy. When do you expect that sort of density of capability?
So as it happens, the production crew from Prometheus consulted one of our founders. We're from University of Pennsylvania. So the point cloud that you see was based on his advice. And what you see over there is basically what we're doing right now. sending the robots out fully autonomously into, now what we haven't done is having them collaborate yet. We'll be doing that next year. But the floating orbs, no, I mean, obviously we're not there yet. What we're trying to do is shrink things down, because in buildings we need to fit through a 36-inch door. So it will get smaller in that respect, but the point cloud that you're seeing, that's what we're generating. Then I can show you some more afterwards.
Yeah. So just a question on the software and hardware. Was there a reason besides the margins that you didn't go into the hardware business? Are you finding the hardware itself quite complicated to the software, where you'd wish that, you only wish that it would do XYZ things better? And then the second question is, what's the weirdest thing you've recorded based on this underground, like that surprised you?
The weirdest thing, that's, I'll have to think about that one. So no, we right from day one, we knew we weren't going to get into hardware. Number one, because that wasn't our core competence. And number two, there were so many good companies out over there building drones, building LiDAR, IMUs, and all the various components. Actually, what you'll see in this box over here is a straightforward Intel media board from Intel Nuke. So what we decided was the fact that we wanted to leverage whatever was already best in class out there. And we've evolved. As better components come out, we literally incorporate that and jettison old technology. So we can evolve and adapt to the best. In terms of the weirdest thing we've ordered, I wish I had a great answer for that. I'll get back to you on that.
Good job not building hardware. That's the right choice.
Yeah. It was said, hardware is hard, and it truly is.
So I saw a video of like the drone flying around the space. It's a video footage. So do you do all your compute locally, directly on your hardware, or is it transmitted through wireless and you have a remote GPU that computes everything?
Critically, we made the decision that everything had to be on board, because you could make no assumptions on communication. In a building, if you turn a corner, in a mine, you kind of go up a slope, you're going to lose communication. If you have if you lose communication with a back-end ground control station, which is doing some of the processing, you're SOL. So we basically say, no, everything's got to be on board, and that is one of the challenges, is to fit everything within the CPU budget that you've got on board. And it's a simple quad-core i7.
Nader, thank you so much for closing the night. Fantastic presentation.